Welcome to lesson 10.2, day 2. Today we are going to continue talking about tangent lines. Today's theorem comes from the idea that when two tangents come from the same exterior point of our circle and they're tangent to the same circle, these two segments are going to be congruent to each other. So what does that mean? So in this example here, we have segment AC. That is going to be congruent to segment, BA, so that we know these two are equal. I like to think about this as the ice cream cone problem. So imagine we have this ice cream cone. You need your cone to have two equal sides so that your ice cream doesn't fall off the top. That's how I like to remember this. So again, I like to call this the ice cream cone theorem. So if we see down below, we have a couple more examples of these tangents coming from the same point. So we know that in order to solve for x, we could set 5x minus 8 equal to 3x plus 2. So we could subtract the smaller value from each side. We end up with 2x minus 8 equals 2. Add the 8 and divide by 2. X is going to be 5 for our first example. Now, sometimes we are not only going to have to solve, we also want to make sure and check, do we need to plug back in? So on this example, again, our two tangents come from point X, so they are equal to each other. And we can subtract 4x from both sides. So we end up with 3x minus 20 equals 1. Add the 20 to both sides. We get 3x equals 21, which means x is going to equal 7 after we divide by 3. Now our segment xy is this one right here. So when we plug back in, 4 times 7 plus 1 is 29 units. Down here for example 3, we want to solve for x as well. So when we solve here, again, we know these two tangent segments are the same. So x plus 22 is going to equal 3x minus 2. Subtract x from both sides, and then add the 2. We end up with 2x equals 24. So x is 12. Now this time, be careful what they're asking you to solve for because they want us to find C to O. C to O is this radius right here, which they didn't give us the value for. However, we know it has to be equal to the other radius value that is given. So we know that segment CO is going to equal whatever the other radius BO is. So we can plug back in 12 for the value of x, and we know that 2 times 12 but minus 3 is 21. So that's how big both of our radii would be on that one. All right, the last one is asking you to find on your own the length of segment MA. Remember what that is equal to. Solve for x first. The second type of problem we are going to see with the two tangent theorem are what we like to call walk-around problems. And what these problems do is essentially notice they are giving us kind of three different ice cream cones. We have T to Q and Q to U congruent. Over here we have U to R and S to R congruent. And then we also have P to T and P to S congruent, right? We have three different ice cream cones essentially on this problem that are congruent. And they're telling us that Q to T is 5, which means Q to U is 5. P to T is 10, which means P to S is 10. And then S to R is 14, which means U to R also would have to be 14. And now we want the whole perimeter of the polygon. So we need to add up for this triangle to find one side, two side, and then our third side. And when we add all of those sides together, 15, 19, and 24, we get the total perimeter of this to be 58 units. On the back side, we have another example here. Notice they did a little bit of the labeling for us, and again, we want the perimeter of the figure. So we know 2 out of the 3 sides. We need to find this third side over here. And we can start by saying, okay, I know that if that little segment's 8.9, so is this little segment. Well, if my big side is 19.9, I can subtract away the 8.9, and I know that this piece here would be 11. And if that piece there is 11, I know that this segment over here also would be 11. Well, that big side is 18.1. I can now subtract away the 11 to get a total of 7.1. And then finally, I know if this is 7.1, so would the other part, the other tangent coming from that same point. And together then, 8.9 and 7.1 make this side a total of 16 units. So the perimeter here, we're going to take 16 plus the length of that side, 19.9, plus the length of that side, 18.1, and together those are going to be 54. On this one, again, we are in charge of labeling. So again, don't forget that officially all of these little tangents are going to have an equal buddy. This will help us, as we solve the problem, know what's equal. So on this first one, they're giving us side RT is 12. Then they are telling us just R to H is 5, which we know means R to D is 5. And then they're telling us all the way from M to T is 21. And we need to find, again, the perimeter of this overall triangle. Well, again, if I know this is 12, I could subtract away the 5 to get my piece here that's 7. And then I know T to A has to match that and be 7. And then 21 minus 7 is 14, which means D to M is also going to be 14. So notice the way we walk around these tangents, hence the name of walk around problem. 5 plus 14 gives us a side of 19. And again, we can add up to get the perimeter, our 3 side lengths. So we get 12 plus 19 plus 21 for a total of 52. Okay, last example together. Again, notice they labeled a couple sides of this time 4-sided figure. So again, we're going to start off by labeling what we know is equal. So we have this little segment, both are 9. Over here, both of these would need to be 5.1, and then 8.7 and 8.7 over here. So we know then if we have that this whole side here is 11.5, if we subtract 11.5 minus that 8.7, we would have a remaining little bit here of 2.8, which means this other side here is also 2.8. So now as we start adding these together, 9 plus 2.8 is 11.8. 9 plus 5.1 is 14.1. 5.1 plus 8.7 is 13.8. And then we were given the 11.5. So that overall perimeter is going to be 14.1 from over here, plus the 13.8, plus the 11.5, and then plus the 11.8 for a total of 51.2. All right, the last one is for you to try. You want the overall perimeter of that triangle. Thanks everyone for watching. We'll work more with these in class.